Lesson 22, question 4 says to determine the final pH of a buffer system where we have a volume of this. So it's not a volume of 1 liter, so I'm probably going to have to be concerned with that. But I'm adding to that 1.2 molar HCl. I'm sorry, the volume of HCl added is 50. But I'm going to have a 500 ml buffer, so I'm going to have to take into account the volume because it's not 1 liter. And I have a 1 molar ammonia, 1 molar ammonium chloride, and a Kb value of 1.8 times 10 to the negative fifth. So the Kb value tells me that my equation should reflect the ammonia acting as a base, which means it's going to accept a proton from the water, leaving me with hydroxide. Okay, so if it was a Ka value, it would be the reverse of this reaction because the ammonium chloride would be acting as an acid, which we know that if this is the weak base, then this is its conjugate acid, and it would have a Ka value, not a Kb value. So in order to make it all make sense, I'm going to have to put everything in terms of moles because unfortunately the volumes are not the same. So if I have a 1 molar solution of ammonia and it's in a volume of half a liter, that gives me 0.5 moles of ammonia and ammonium. That's what I'm starting with. Moles. And I'm not starting with any of the hydroxide, but it's a buffer problem, so I don't necessarily need to know that. This is kind of what I'm solving for. Now I'm going to add HCl. I need to know how many moles of HCl I've added. So that should give me a value of 0.06 moles of HCl added. Now I'm adding a strong acid to this problem, so the HCl is going to react with the OH minus to form water. You can probably hear Anderson playing with transformers in his room, hooping and hollering, and this will shift the reaction . I have that backwards. I got distracted by the hooping and the hollering. The HCl is going to react with the ammonia because that's the active piece right there. So it's going to react with the ammonia to form ammonium ion. So the reaction will shift to the right. Okay, we're only looking at the base and the acid when we're looking at how the buffer protects the reaction, if that makes sense. Because these are the two components that are present. So it's either going to be the base or the weak base, weak acid, or its conjugate that's participating in the buffering. So the reaction is going to shift to the right, meaning that it's going to consume this many moles of ammonia and produce that many moles of ammonium. So that's going to leave me with 0.44 and 0.56. And at this point, I am not told that I can assume the volume is negligible. So I'm going to take the 500 and the 50 and get a new molarity. Okay, so I'm going to divide 0.44 by 0.55, which is the new 550 milliliters, and 0.56 divided by 0.55, and I should get these new molarities right here. Now, if you remember, I told you there was two forms of the equation. So there's the POH is equal to the PKB plus the log, and then I said it was hubbub. But it's still products over reactants. That part's not changing. So pH, the negative log, or POH, sorry, and I'm going to take the negative log of the KB plus the log of the conjugate acid divided by the weak base. So I'm going to end up getting a PKB value of 4.74, and I'm going to add to that 0.11, which is going to give me a POH of 4.85. But I need to know the pH, so good old formula of subtracting 14 minus 4.85 gives me a pH of 9.15. Okay, final answer. We'd expect it to be basic because it is a 1 kb. There's a kb and it has ammonia. Okay, so it's written in terms of a base.